All right, stoichiometry in a nutshell. We're going to talk about stoichiometry, talk about the mole, different variations of doing calculation involving stoichiometry in the mole. And we're also going to talk about numbers, how to deal with small and big numbers, how to know what to write that shows up in your calculator, because all these things are going to come into play when you're writing answers. So let's get started with the number part first. So we're going to get started with what's called significant figures. These are the numbers that you acknowledge from a measurement. So when you see a number like this, for example, a lot of students will write all these values in that shows up in the calculator because that's what shows up in the calculator. You're not supposed to do that. The only numbers you should write are the ones that are significant. So the question is, how do you know which numbers are significant and how do you maintain the size of the number? Like for this example, if these zeros are not significant, can I just write 7? No, because then I'm not acknowledging all these zeros. So that's where scientific notation comes in. We're going to talk about that as well. So let's first talk about significant figures. So all non-zero digits are significant. So what does that mean? Numbers 1 through 9. Any of those numbers are significant. So the question is, okay, what is not significant then? Zeros. But there are certain times that zeros are significant, and that's where all these rules are going to try to come and explain. When is a zero important enough to write? So zeros between two significant figures are themselves significant. Sandwich effect. So if you have this, for example, you have 1, 2, 3, 4, 5 significant figures because these zeros are significant. And that's because they're between two significant values, which are what the numbers 1 through 9 represent. Zero is significant if they follow a number and a decimal point. So if I write 0.007, these zeros are not significant because even though they follow a decimal point, and this is supposed to be 0, they do not follow a number yet. So when does 0 become significant? If I put them after the number and a decimal. So here's your decimal point. So these zeros, not important. These zeros are important. So you do have to write these into your final answer. And if you're to write this in scientific notation, you're going to move decimal point 1, 2, 3 times to the right, which means this becomes 7.000. And because you move to the right, your exponent goes down 3 times, so 10 to the negative third. Remember, you start at 10 to the 0, wherever your decimal point is. And then each time you move it to the right, your exponent goes down. Each time you move to the left, like let's say for this example, since you don't see a decimal point, it's all the way here. Whenever you don't see it, it's at the end. So you go 1, 2, 3, 4, 5, 6. So this would be 7 times 10 to the 6th. So why is it 10 to the 6th? Because you moved over 6 times to the left, which means if you start at 0, your exponent goes from 0 to 6, and that's why it's 7 times 10 to the 6th. Notice I didn't write any zeros into this answer. Why? Because none of these zeros are significant. Here, I did have to write these 3 zeros because they are significant. If I do not write those 3 zeros into my answer, I am wrong. So when a number comes before a decimal point, all the zeros are significant. This is kind of like a catch-all. So if I have 7.0000, I could go on zeros for 1,000 miles here. All of them are significant. Here, 7.00, all the zeros are significant. So you have 3 sig figs here. You have 1, 2, 3, 4, 5, 6, 7 sig figs here. So anytime a number is before a decimal point, everything you see is significant. So yes, you would have to write all those numbers down if that was really the case. So we talked about scientific notation briefly. So what is it? Used to represent values using a coefficient and exponent. So what's your coefficient? It's the number before your multiplication symbol. Your exponent is this number here, 10 raised to whatever power. Key features are you can only have one number to the left of the decimal point. So you cannot have a 0 to the left of the decimal point. Like let's say for this example, we wrote 0.7000 times 10 to the negative 2 because I only moved it over twice, once, twice, instead of 3 times, which is what I'm supposed to do. You'd be wrong. You cannot have a number to the left of the decimal point that is not 1 through 9. So this value has to be 1 through 9. Zeros are not accepted. All right, scientific notation, multiplication, division. Multiplication, so what do? You multiply the coefficients together, which would be 2 times 4. That's just simply 8. And then you add the exponent. So it'd be 8 times 10 to the 3 plus 5, 10 to the 8th power. How many sig figs? Well, only 1, because that's what your answers have. For division, same concept. You divide instead of adding in this situation. So 8 divided by 4, which is basically equal to 2. And then you, instead of adding your exponents, you subtract them. So it'll be times 10 to the 4th power, because 6 minus 2 is 4. So those will be your answers if you're multiplying or dividing involving scientific notation. For addition and subtraction, a little different. You have to make sure both numbers have the same exponent in scientific notation. So if you notice here, it's 10 to the 3rd, here's 10 to the 2nd. You can't do the math on this. So what do you do instead? You make 0.10 times 10 to the 2nd into 0.01 times 10 to the 3rd. For those wondering, how did I do that? All I did was move the decimal point one more time to the left. And for those wondering why you do that, because you want the exponent to be 3. So how do you get to 3? You have to move the decimal point to the left because you're starting at 2, and each time you move to the left, your exponent goes up by 1. So you go from 2 to 3. If you had moved it to the right, you would have ended up with 0.1. Let's just move it to the right to show you. So it'd be 1.0. Since you started at 2, you move to the right, so you subtract 1, it'd be 10 to the 1st. That's not going to work. We need to have the same exponent for both values before we do the math, so that's when we move to the left. So your answer, now that you have the same exponent, now you can add the numbers together or subtract them, whatever the case may be. This plus this, and then your exponent is 10 to the 3rd because both of these are 10 to the 3rd. So your answer is 5.41 times 10 to the 3rd. So for addition and subtraction, you want to make sure your exponent is identical before you add or subtract. All right, let's try a couple questions, see if we can figure this out. So for this one, what is it in scientific notation? Well, you only have one sig fig, right? Because there's no zeros after, so they're not significant. So move it over 1, 2, 3, 4. So it'd be 9, not 9.0, just 9, because you only have one sig fig. If you put 9.0, you're implying there's 2 sig figs, so that's a no-no. Times 10. Well, how many times do we move it? 4 times to the right, so it goes 10 to the negative 4. Here, your decimal point's not at the end, it's right here, so move it over once, twice, 4.5. Question is, what do I do with the zeros? Well, remember what I said, if the numbers before a decimal point, everything thinks is significant, so these zeros have to be written into your answer. So you have to write 1, 2, 3 zeros, otherwise you would be wrong. And that would be 10 to the 2nd power, because we only moved it twice. Once, twice, that's why it's 10 to the 2nd. Third one, 2 sig figs, 1, 2, 3. Well, you don't need the 4th, sorry. 9.8 times 10 to the negative 3, because I moved it over 3 times to the right. For this one, you have 4 sig figs, because the zeros are after a number and a decimal point. They're all significant. Move over once, twice, so you end up with 5.000 times 10 to the negative 2. Because you moved it over twice to the right. Last one, 3 sig figs. Decimal points at the end because we can't see it. 1, 2, 3, 4, 5. So you end up with 7.89 times 10 to the 5th. And that's how you do those values. All right, determine the correct number of sig figs in math. There is a system. For multiplication division, you could only have as many significant figures in your answer as the least significant value. So what does that mean in English? So you look at all the numbers you're multiplying together and you identify which one has the fewest sig figs. Here we have 3, here we have 2. 2 has fewer sig figs, so our answer can only have 2. If there was 4.56 times 1.4 times 1 with only one sig fig, our answer could only have one number in its answer. So instead of 6.4, which is what this, so this is what you get when you multiply them together. You got to change it into the correct sig fig, which is 2. That's what this is. So it's the correct answer. But if hypothetically you had this third number to multiply by times 1, which only had one sig fig, your answer would go from 6.4 to having to be 6 only, because that's how many sig figs your answer can have. So that's how you do it for situation where you're multiplying. Dividing, same concept. We have 1, 2, 3 sig figs here. We have 3 here, so our answer also has to have 3. So how do we do that? Well, we're just going to go 20 divided by 4, which is 5. 5 is not the correct answer because I have to have 3 sig figs. So where are the other sig figs? Your zeros. Here, 198 divided by 9. So 9, that's 1, 2, that'll be 18. So how many sig figs can my answer have? Well, look at it. You have 3 here, 1 here. How many sig figs can your answer have? As many as your least significant value, which in this situation would be just 1. So that's not going to work. And I think I did the math wrong for this. So let's just do it real quick. 9, 28, sorry, not 18. So how do we change this into the correct number of sig figs? Only 1 sig fig. So you look at the one that's the 1 sig fig. Look at the number after to decide if you have to round up or round down. 8 is bigger than 5. 5 or larger, you have to round the number up. 4 and below, you round it down. So here, 28 means your answer just becomes 30. 30 only has 1 sig fig. And that's because your answer can only have 1. And if you want to be on the safe side, you can also go 3 times 10 to the first, which also only has 1 sig fig. All I did, decimal point once to the left, making sure I only have 1 sig fig like my answer is supposed to, and I'm done. Let's say, for example, this was 24 instead, for the sake of argument. So what would your answer be here? It would be 20. Why? Because 4 is less than 5. Remember, 5 and above, you round up. Anything less, you keep as is. So instead of making this into a 30, you make it into a 20, which, once again, 2 times 10 to the first is the other way of writing this. For addition and subtraction, just worry about how many sig figs are to the right decimal points. The numbers to the left do not matter. We only worry about what's to the right. So look at your 3 values. You have 2 sig figs, 1 sig fig, 3 sig figs. So guess what your answer has to have? 1 sig fig. Do I care about how many numbers to the left? No, I do not. I only care about what's to the right. So your least precise measurement is 18.0, which only has 1 sig fig to the right. So your answer becomes, so this is when you do the math, put in your calculator, you get 31.123, and then you put the correct number of sig figs to the right is 1. Why? So here's how many sig figs I could have to the right. Look at the number afterwards. If it's less than 5, keep it as is. If it's greater than, round up. That's how you figure it out. All right, so let's try some questions. In this situation, how many sig figs can my answer have? Well, you have 1 to the right, 2 to the right, 3 to the right, and 1 to the right. Excuse me, 0 to the right. So that means that your answer could have 0 numbers to the right decimal point. So 7 plus 3 is 10, plus 5 is 15, minus 12 is 13. And that's it. My answer is 13. I don't put 13.0 or anything else because this number has nothing to the right decimal point. Next one, same logic. You have 1 sig fig, 2, and 4. So my answer could only have 1 sig fig to the right decimal point, which becomes 29.0. As shown, 1 number to the right decimal point. Third one, 9 times 10.0. Here, it's not addition subtraction, so it's total sig figs. We have 2 sig figs, we have 3. So my answer could only have 2 because this has the least number of sig figs. So 9 times 10 is 90, which if you look at it, it's only 1 sig fig, but guess what my answer is supposed to have? 2. So how do I fix that? 9.0 times 10 to the first. Decimal point once to the left. That's where you get the 10 to the first power. Y point 0? 2 sig figs, like your answer is supposed to have. Next one, same thing. How many sig figs? You can only have 2 in your answer. 3 times 9 is 27. You can write 27 or 2.7 to the first. Either one's correct. All right. Now that we move on from the numbers, let's get to balancing equations. These are the rules for balancing equations. First thing, you count the number of atoms on both sides. You treat polyatomic ions as a single unit if it does not react. So what does that mean? You have PO4 on the left side. Let's say calcium phosphate. Well, let's just call it PO4. Don't worry about what it's attached to. And you have a PO4 on the right side. Instead of looking at this as 1P and 4 O's, 1 PO4, 1 PO4. We balance it that way. And you'll see what that's going to look like in a minute. 2, use coefficients to balance elements one at a time. You can only balance, place numbers in front of the chemicals. So you can only do this, You can't do this, make this 4 into an 8. You can't put a 2 here to make it cute. Only thing you're allowed is numbers in front only. 3, balance alphabetically, it just works. But make sure you do H and O last in that sequence. So your last two elements you always balance is H and then O. Why? It just works out that way and it gives you the right answer most of the time. And the last rule, if you have an odd number of an element on one side of the arrow and an even number on the other side, double the odd side. And I'll show you what that looks like as well. All right, so let's start with some balancing questions. So balance alphabetically. Remember, H and O is last. So what's my first name in the alphabet? C. C is attached to 3O. It's CO3, a polyatomic ion. I have one CO3 on each side. It's balanced. So I move on to the next letter. What's the next letter? Na. Why not H? Because H and O is always last. So 2 NAs, I'm just going to balance it. Do I care what happens to the O and H? I do not. I'll deal with it when it's time. And now it's time because the next letter on my alphabet is H. You have 2 plus 2, that's 4 hydrogens. Here I only have 2 hydrogens. So here's 2 times 2. You multiply the coefficients times the subscript because you have 4 oxygens and 2 oxygens. How many oxygens here? 2 oxygens. I know what you're saying. That's 2 plus 3. That's 5 oxygens. Yes, but remember we counted CO3 as a unit. That way we don't have to worry about it ever again. But if you want to verify, 3 plus 2, 5 oxygens on that side as well. All right, let's go to the next one. So here you have 2 nitrogens. Here you have 2 nitrogens, so that's fine. 2 O's, 5 O's. This is the odd versus even situation I was talking about in Rule 4. Double the odd side. What's the odd side? This one. Make this into an even value. It's the only way to balance it. So now we go back and balance it. So we change our ands from 2 to 4. So we need to fix that. And our O's, 2 times 5 is 10. So we put a 5 here, and now we're balanced. So that will be the balance equation. Next one. We have 1, 2, 3, 4 carbons. So 4 carbons. We have 3, 5, 7, 10 oxygens. 10 oxygens. And then our O's, you notice that you have a 5 in front of here. So 8 plus 5, 30. That's an odd number. Odd versus even again. So how do you fix that? Double everything except O2. When you're doing a combustion reaction, it just works out. So instead of having one of these, I'm going to make 2. Instead of 4, I'm going to make 8. Instead of 5, I'm going to make 10. By doing it this way, I don't have to go back and fix these elements because they're still balanced. So now I can worry about the O's by themselves. 16 plus 10 is 26. So then here, let's put a 13 in front of this to give you 26 as well, and that gets balanced. And then the next one, same thing. We're going to balance alphabetically. So you're going to start with Mg. Which is already balanced, and then you go to NO3, and for NO3 you could see you have 2 here, so put a 2, then balances the N, and then there's your 2 for it, and everything else gets balanced. Moving on from the mole, from balancing to the mole, the next concept is dealing with a number that represents the number of atoms typically in a molecule or an atom. It's a fairly large number. And for our purposes, it's not the little furry animal you see. It's just basically a value. So just like when you think of a dozen, you think of 12. When you think of gross, you think 20. Ton is 2,000. When you hear the word mole, you're going to think of this number, 6.2 to the 23rd. It's a very large value, as you can see with all the zeros in place. So it's a very significant value because it represents how many atoms or molecules are in 1 mole of a substance, which, if you put it more simply, the periodic table has masses underneath each symbol. For example, the mass of carbon is represented by 12.01. Now, that's the mass of a single atom of carbon. But what if we're talking about a mole of carbon? Well, a mole of carbon weighs 12.01 grams. Yes, it's the same number, just a different unit. The 12.01 grams of carbon has exactly 6.02 times 10 to the 23rd atoms inside of it. That's the way this number works out. So 1 atom of carbon has 12.01 AMU as its mass. 1 mole of carbon has a mass of 12.01 grams and has 6.02 times 10 to the 23 atoms inside of it. So that's a large number of atoms. So in chemistry, is the number of atoms or molecules in 1 mole. For example, 1 mole of carbon, 1 mole of lithium, both have the same number of atoms. So any mole of any substance has that many atoms. Now the key here, this is a single atom, is represented by the word atoms. single element. So when we're talking about lithium or carbon, which are single elements, we're talking about that. But what if we're talking about a compound? What do we do then? Well, instead of using the word atoms to represent, we call it molecules. So now we're designating the difference between an atom and a molecule is basically the fact that an atom has a single element and a compound has two or more elements inside of it. So for example, 1 mole of CO2 and 1 mole of NO2 has 6.02 to the 23rd molecules. So notice the same number, the only difference is the units. So single elements have that many atoms and compounds have that many molecules, same exact value. Mole and weight, you can't really measure the mole directly because there is no balanced or equivalent piece designed for it. But what you can do is get the mass of a substance and go from grams to moles using the periodic table, what's called the molar mass. So what is the molar mass of a substance? Well, that's just the number below every symbol, like we said earlier. So everything in the periodic table is exactly 1 mole. All those masses you see in the periodic table equal exactly 1 mole of that substance. For example, 12.1 grams of carbon is equal to 1 mole, 1.001 grams of hydrogen is equal to 1 mole, and so on and so forth. All right, so let's go through some conversions, things you can use the mole to calculate for. So what if you want to go between moles and volume? Like you want to know how many liters are in 1 mole of a substance or vice versa, how many moles are in a liter of a substance. So 22.4 liters equals 1 mole. This is only for gas. This does not apply for anything else other than gas. So if you have a solid or liquid, this value is irrelevant. You only apply it when it's a gas. So what's the volume of 4 moles of hydrogen? Well, we know that 1 mole of hydrogen has a specific mass. So what is 4 moles of it equal? Well, if you know the relationship is that there's 22.4 liters in exactly 1 mole, then you can make the assumption that you can make a T-chart. Now, a T-chart is just a simple way of organizing information for ourselves. So whatever we started with, we put in the upper left-hand corner. So in this case, they gave us 4 moles of hydrogen. We're going to put it here. And we know the relationship. There's 22.4 liters in a mole. Now, we're trying to go from liters to mole. In dimensional analysis, what that requires us to do is put whatever we're looking for on top. So we're looking for liters, so we're going to put on top, and whatever we are trying to go from on the bottom. So when we multiply this together, we get 89.6 liters of H2. So that's the volume of exactly 4 moles of hydrogen. Now, you could have plugged in any different chemical. You could put hydrogen, nitrogen, fluorine. If you have 4 moles of it, it's going to always have a volume of 89.6 liters. That's important to note. So the density of the chemical doesn't matter when you're going from moles to liters. How many moles are in 44.8 liters of helium? Same thing. You just put 44.8 liters of He. We're going to put the symbol this time. You could on the one above it too. Just forgot to. There's 22.4 liters in 1 mole. So there's exactly 2 moles of helium in 44.8 liters of it. So once again, you could have plugged any other substance, oxygen, fluorine, it would have all given you the same value, 2 moles being what it's equivalent to. What if you want to go between moles and grams? Well, we're going to use the molar mass in the periodic table. So 2 moles of CO2. So what is the molar mass of CO2? Well, first let's put our given information, make a little T-chart like we usually do. And now let's get the mass. So we know 1 carbon weighs 12 grams. We know oxygen weighs 16 from the periodic table. There's 2 of them, so that's 32. So the total molar mass is 44 grams per mole. That's the units for molar mass, grams per mole. So what do? We need to put 44 grams either on the top or bottom and a mole on the top or bottom. So how do you know which one? Well, you're trying to go from mole, so put it in the bottom. Put 44 gram, which is what you're looking for, on top. So we end up with 88 grams. So all we did numerically, I should have done it for the other ones, the units you're starting with, you're canceling out, and then you multiply the numbers together. 2 times 44 gives you 88 grams. Here, same thing. Notice the units cancel out. You're left with 44.8 divided by 22.4. That's where you got the 2 from. And then the units is left over is the mole. And same thing with this one. Mole goes away. You're left with the unit you're looking for, 4 times 22.4. So that's how the math and the units work out in this calculation. All All right, how many moles are in 8 grams of CH4? Same thing, I'm going to put 8 grams CH4, make our usual T-chart, molar mass 12 plus 4. Each hydrogen weighs 1, and there's 4 of them. Carbon's 12 from the periodic table, so it's a total of 16 grams per mole. So we're going to put 16 grams on the bottom. Why? Notice how they cancel out. That's how you know you did it correctly. 1 mole on top. So 8 divided by 16 is just nothing more than 0.5 moles of CH4. Converting between moles and atoms or molecules, there's exactly 1 mole and 6.2 times 10 to the 23rd atoms or molecules. So how many atoms are in 3 moles of carbon? Well, we're going to put our 3 moles on our per left-hand part of the T-chart. Now, relationship, here's our relationship. So which one goes on top? Well, you know 1 mole has to go on the bottom, right? So 6.02 times 10 to the 23rd. And since we're talking about a single element, we're going to call it atoms. 2 times 6 is 18 times 10 to the 23rd. I'm going to do it without a calculator. I'm going to ignore the 0.02 for our purposes. The concept's really the big thing here. We don't want to worry too much about the exact value at this point. This is not scientific notation. Remember, you can't have 2 numbers to the left decimal point. And decimal point, if you don't see it, is always at the end. So put it here. So what we're going to do is move it once to the left. And when we do that, we get 1.8 times 10 to the 24th atoms. And there's our value. That's our answer. Notice once again, the units cancel out. So you could always check if you did it correctly. The units cancel out, and whatever you're left with is what you're looking for. And that's exactly what happens here. All right, now we have 1.2 times the 24th molecules. So now we're dealing with a compound because they're saying molecules, right? Same thing, T-chart as usual. So we know there's 6.02 times 10 to the 23rd molecules in 1 mole of CO2. So look, units cancel, units cancel. We left what we're looking for. 1.2 divided by 6, that's nothing more than 0.2, right? If you want to do it another way, you can make this 12 times 10 to the 23rd. All I did with decimal point once to the right, which makes the exponent go down by 1, divided by 6 times 10 to the 23rd. So 12 divided by 6 is just nothing more than 2 times 10 to the 0. If you did it with the decimal, it would have been 0.2 times 10 to the first, right? Because 24 minus 23 gives me 1. So 0.2 times 10 to the first. Then you move decimal point once to the right to make a scientific notation, and you get the same answer. So either way, you would have got the same value. It just depends on which route you feel more comfortable with, decimals or making it into something more manageable. I always try to make it more manageable for myself by making the top number 2 digits, but it's up to you how you want to approach it. All right, stoichiometry basically allows you to go from the amount of one chemical to another. So it basically allows you to go from a recipe and then modify it based on the number of people available. So for example, let's say you have a recipe for 5 people. Now you get 10 people showing up. What do? Well, you can't modify the recipe. You have to have the same ratios of substances in your ingredients list, right? What you're going to change is the amount that you're making by changing the amount of the quantities of stuff that you need. For example, if you're trying to make enough for 4 people, and let's say that you need 2 chickens for 4 people. Okay, so for every 4 people, you'll need 2 chickens. What if you need to make it for 8 people? Well, you're going from 4 to 8. That's doubling the number of people. So that means you need to double the amount of chickens. So instead of using 2 chickens, you're going to use 4 chickens. Now, that's how it basically works. But for our purpose, let's get into the actual chemistry. It's typically one reactant controls the amount of products produced, which is called the limiting reactant. So any chemical reaction, you're always going to run out of one chemical before every other one. That's called our limiting reactant. The one that's left over is going to be called the excess reactant. Those are 2 quantities. So here's the steps for doing stoichiometry. There's a separate video that goes into detail on how to do this with more examples I'm going to show you right now, but so at least give you the basics. So the first thing you're going to do, the question does not give you moles, you're going to go to moles. So how do you go to moles? Divide by the molar mass, and you get moles. 2, divide the moles of each reactant by the coefficient found for that chemical in the balance equation. Now this may seem really confusing at first, but once you see it, you understand how to better do it. So in this situation, you're going to take the reaction, whatever it is, and you're going to divide by the coefficients to go from the moles of the chemical that you figure out in one into a number. And that number is going to help you identify the limiting reactant. You're going to multiply the value from whatever you get here by the coefficient for the chemical you're looking for in the balance equation. And these two steps are the ones that are always required for stoichiometry. The first and last step really depends on what they're asking you and what they're giving you. And the last step is if the question is asking you for grams, to multiply whatever you get in 3 by its molar mass. So this may seem really confusing, so let's go over into an example of it. So here's an equation. It's already balanced for you. You have 28 grams of nitrogen reacts with 12 grams of hydrogen. The way you can tell this is a limiting reactant question is because you have masses for both reactants. Sometimes we get questions where they just give you mass of one chemical. In that situation, that is your limiting reactant. You don't have to worry about doing all these steps for both chemicals like I'm about to show you. You just do it for one chemical all the way through to get your answer. And sometimes they'll tell you 20 grams of nitrogen with excess hydrogen, which once again is narrowing it down how you do the math. Now, the steps are going to be identical either way. The only thing is you're going to take one chemical through the journey or both. So in this situation, step one, you're going to go to moles of all the reactants. So we have two reactants. So we're going to take our 28 grams of nitrogen they gave us, divide by the molar mass from the periodic table, right? 14 times 2. And that gives us our molar mass. So now we're going to go from grams to moles. So there's 1 mole of nitrogen. And then we have 6 moles of hydrogen. Same thing, 12 grams of hydrogen divided by the molar mass in the periodic table. 12 divided by 2 gives you 6 moles. Then what you're going to do is take these numbers and you're going to divide by the coefficients in the reaction. So here, there's no coefficient, assume it's 1. For hydrogen, it's 3. So I'm going to take the 1 I got here and divide it by the coefficient, which is 1 from up here, right? So 1 divided by 1 gives you 1. We can do the same thing for the other chemical. 6 divided by the coefficient, which is 3. That gives me 2. Whichever one of these two is your small number, that's your limiting reactant, which is this. That's the one you take to step 3 and 4. So the only point of doing step 2 is to identify what your limiting reactant is if necessary. Let's say hypothetically you didn't have a limiting reactant question, just one of these, meaning that it just said 28 grams of nitrogen with excess hydrogen. How would this question be different? The only difference is this part would not be necessary. You just go from here to here to here to wherever your destination is. So that's the only thing that you would modify, is that you'd only be doing it for one chemical all the way through, but the same steps are required. Step 3, you're going to multiply by the coefficient for what you're trying to go to. So in this situation, we're going to ammonia, right? So what's the coefficient for ammonia? 2. We're going to take the 1 that we got here, and we're going to multiply by the coefficient what we're looking for. Notice at this point, there are no units, right? The units all canceled out. So you just have with a number. So when you multiply by the 2 moles of ammonia, you go to moles of ammonia. So now you have 2 moles of ammonia. And in step 4, because you're looking for mass, we're going to take that mass, the molar mass from the periodic table, excuse me, and then multiply by that 2 moles. So 2 moles, 17 grams per mole, you get 34 grams of ammonia. That's your final answer. So that is the mass of ammonia, and that's how you solve for it. All right. Empirical formula is the other concept we need to be familiar with. This is basically trying to show you the ratio of elements in an unknown compound. So this is what happens in a laboratory. You do an experiment, you get some data, and what that data does, it gives you what's called the empirical formula. It tells you the ratio of one element relative to each other, but not necessarily the actual identity of the chemical. That's what's called the molecular formula. I'll show you how to do that as well. But let's first talk about the empirical formula. So what is the empirical formula? It's just the smallest ratio. So if you're doing the empirical formula for this thing, what's the smallest ratio of these elements relative to each other? 3, 6, and 1. How did I get those? Divide everything here by 2, all right, to get the smallest ratio. That's what empirical formula is. In the general sense, it's just the smallest ratio of elements in a compound. So if you were to solve for empirical formula without anything else besides this, all you're doing is just this, and you're done. Of course, it's never going to be that easy. All right, let's determine empirical formula for a couple of them just to make sure you understand the concept. Here, divide by 2, you get CH2. For this one, notice you can't divide by 1 or 4 to get a different value. So this is your empirical formula. It's your smallest ratio. You can't get decimals for this. Here, 2 goes in 2 once, twice. You get it MnO2. Here, smallest ratio would be determined by dividing everything by 11. So that gives you 1. That gives you 3. 33 divided by 11 is 3. And 22 divided by 11 is 2. So your answer becomes C2H03. All right, so now how about empirical formula with using some of the data? So they're going to give you typically percents, and what your job is to do is to take the percent symbol and change the grams. How do you do that? Just get rid of the percent symbol, put G in its place, and that's all you're doing. There's no other complicated math involved there. Just change the percent to a G, and then you go from there. Convert the grams to moles by dividing by the molar mass. Typical route to get our moles. Divide each mole value by whatever the smallest one is. So you're going to have multiple mole values at this point for each of the chemicals inside that unknown. Divide all of them by whatever the smallest mole value is. If the values you get from step 3 is not whole numbers, then you multiply by number to make it whole, usually 2 or 3. And this make more sense once we do an example. So what's an empirical formula for a compound is 25.9% nitrogen, 74.1% oxygen. First thing, percent to grams, right? Done. That's all you gotta do. 2, go to moles. So here, all we did was divide by the molar mass in the periodic table. Notice a single element. Even if they're diatomics, please don't, make this N2 and O2 and make this 32 and 28. Don't do that. It's just a single element molar mass, always. So 25.9 divided by 14 gives you 1.85. It gives you 4.63. Which one is the smallest mole value? This. Divide both of these by that value. So when we divide 1.85 by 1.85, we just get 1, right? And if we divide 4.63 by 1.5, we get 2.5. Notice this is not a whole number. And no, you cannot round this to a whole number. And I want to be clear about this. Do not round at all until this point. And then at this point, don't round if your value is between 0.2 and about 0.8, like, 1.2 to 1.8, 4.2, whatever. The point is the decimal is what you're focusing on, right? If the numbers are between these two, 0.2 to 0.8, do not round. You need to multiply by your value. But let's say you get 2.96 instead of 2.5. Yeah, round. Great. What if you get 1.1? Yeah, round 1. That's fine. Any other value, don't. But make sure you don't do this rounding until this step. Do not do it over here. Do not make this 4.63 a 5. Carry it to 3 digits at all times, not 2 digits, 3. Don't make this 1.9, make this 1.85. Always carry it to 3 digits. The reason is if you try to get cute here, you're going to make a mistake in the next step because you've rounded unnecessarily. So be careful with that. So we're going to multiply both numbers by 2 because that's what makes this a whole number. So we get 2 and 5. So what's our empirical formula? And 205. You did all this work just to get that formula. And the reason we got this is because we have to multiply both of them by 2 in order to make this whole. So yes, even though you only need to multiply by this, you have to do it for all chemicals involved, not just the one that you're trying to make a whole number. Otherwise, your answer comes out wrong. All right, let's go over molecular formula. It's usually just a multiple of your empirical formula that can also be the same as your empirical formula in rare circumstances. So notice here the only difference is they're giving me the molar mass of this unknown chemical. So I'm going to do the same things I did a second ago for empirical formula. I'm going to take both of these and to get our empirical formula. So divide by the molar mass. I get these 3 values. I'm going to divide all of these by 2.021. Why? Because this is my smallest mole value. So when I do that, I get 1, 1, 2. Great, all whole numbers. I don't need to sit there and do anything cute by multiplying by another value or something. So your empirical formula is just this. Now, you're asked for the molecular formula. So what do you need to do? What you need to do now is get what's called the empirical mass. That's the mass of all the elements in this compound. Basically, the molar mass of the compound. You're going to take 35.5 plus 12 plus 2. And then from there, that's what you get. It's called empirical mass. So here's our empirical mass. That's the 49.48 I got by doing these numbers up here. And this number they give you, the molecular mass. You take that, divide by your empirical mass, you get a number. That's the number you need to multiply this by to get your final answer for the question. So you have to do this step when asked for molecular formula. So once again, take the molecular mass they give you, divided by the empirical mass based on the formula you came up with, get a number, take that number and multiply by your empirical formula. And when you do that, you get Cl2C2H4, and that's your final answer. Now you're done. All right, moving on to percent composition of compounds. Percent of an element inside of a compound, this is basically the element's mass divided by the total mass of the compound. It's pretty simple. Like here, the molar mass is 18, right? 16 from oxygen, 2 from hydrogen, 18. So if you're trying to figure out the mass percent of oxygen, all you have to do is take the molar mass of oxygen, which is 16, divided by the total mass, the total molar mass, which is 18, and multiply by 100. And when we do that, we get 88.9%. So 88.9% of this compound is going to be oxygen. So what is hydrogen going to be? Well, you could go through the math, 2 divided by 18, or remember that your total percent has to equal to 100. So hydrogen's percentage really is 100 minus 88.9%. That's all you have to do, which is basically what, 9.1%, sorry, bad math, 11.1%. All right, question, here's another example of it. So what's the mass percent of carbon? Here's the molar mass of the total compound. So all I have to do is just do 12, and there's 2 of them, right? So this is 24. So take 24 divided by 46.07 times 100. You get your percentage, which looks like it's about 52.14%. And you can see how the math plays out exactly to give you 52.14%. What about mass percent of hydrogen and ethanol? Same thing. Ethanol is the C2H5OH. So 2 different ways, right? We could do 100 minus 52.14, and we'd get our difference. In this situation, you actually have, 3 elements, so I can't do that. You can't do subtraction because your total percentage is made of carbon, hydrogen, which is basically 6, and oxygen, which is 16, so that's not going to work. So what we have to do is actually do the math. So we're going to take the molar mass of hydrogen, which is 6, divided by the total mass of the compound, which is 46, and get our answer. So 13.13%. Now, if I were to figure out the mass percent of oxygen, now I could just do that subtraction, right? You could do 52.13 minus, 52.14 plus 13.13 minus 100%, which will give you the percentage of the answer, or you do 16 divided by 46 times 100, which is 34.73%. Either way is fine. So that's how you do mass percentage. You take the mass of the element, and that's based on the subscripts, right? Even though carbon's 12, there's 2 of them. Even though the hydrogen's 1, there's 6 of them. Divide by the total molar mass. And that'll give you the mass percent. All right, lab-wise, you need to know 2 concepts, percent yield, which is basically going to be the actual mass they give you. So in the laboratory, you do an experiment, you get the actual amount from the lab, right? You do your experiment, you get 4 grams as your actual amount of product. But your theoretical is what you expect it to happen. That's usually solved using stoichiometry. And what you do is you do actual divided by theoretical times 100, and that's what's called your percent yield. That's how much of the substance you got compared to what you expected to get. So it's just basically a check on accuracy. The smaller the number, the worse you did, because you want to have a high percent yield, right? Because that means you did the lab really well. The other one that you're going to typically do a lab is called percent error. Percent error, once again, actual minus theoretical divided by theoretical. So there's the actual and theoretical again. The only difference here, we got to subtract the actual mass they give you, or the one you got from your laboratory, minus what you expected to get, which is called your theoretical, divided by that theoretical, and you do the absolute value for this. So that means your number has to be a positive value, right? You can't get negative percentages. Sorry about the lines being all crooked. I'm trying to draw 2 vertical lines. I'm doing a horrible job of it. So that's how you get your percent error. All right, the Next thing is stoichiometry within a compound. So this is really where it gets interesting on AP exams because they do a lot of this. Instead of going between two chemicals stoichiometrically, you go between the elements inside the compound. So instead of using coefficients, which you get from the balance equation, use subscripts for this. So how many grams of hydrogen are exactly 5 grams of H2O? So how do you figure this out? So you want to know how much of this 5 grams comes just from the hydrogen. So what do? First thing you do is go from from grams of water to moles of water. So when we do that, we get 0.278 moles. So that's how many moles of water we have. Next, what we're going to do is go from moles of H2O to moles of H. So how do we do that? So in 1 mole of compound, that's always going to be the case, by the way. When you do this calculation, it's always going to be 1 mole of the compound. Then you put the subscript here as your value for that other substance you're looking for. So the ratio, where do I get it from? Right there, the little 2. So there's 2 hydrogens for every 1 H2O. So you multiply by 2. You get 0.56 moles of hydrogen, but they're not looking for moles, right? They're looking for grams. So now I have to do is go from here back to grams. I know you're saying it's pretty redundant in this, doing all this over and over again like this, but you have to. So this is how many grams of hydrogen there is. How many grams of oxygen? Just do the math. 5 minus this, that's your oxygen. Or you could do all this again for the oxygen if you wanted to, but I suggest just subtracting. All right, how many grams of Na and O are in 10 grams of Na2O? First thing we're going to do, go to moles, right? 0.161 moles of Na2O. Then we're going to go from the moles of Na2O to moles of Na. So 2-to-1 ratio. And that's because there's a 2 right there. So there's our moles of Na. Then we're going to go from moles of Na to grams of Na. The way we do that, multiply by the molar mass. So now we have grams of Na, 7.42 grams. Now, if I was trying to figure out the oxygen, just take your total mass. You know 7.42 is Na, so guess what does the rest have to be? That's right, oxygen. So that's where you get the 2.58. So that's how you use stoichiometry in the compound to go between 2 different chemicals inside of a compound. All right, now we're going to put this together and do what's a typical question, which is you're trying to figure out the identity of an unknown using this kind of data. So you have 36 grams of an unknown compound, typical scenario, containing 3 elements, CHO. You don't know how many C's, how many H's, how many O's in the compound. You just know there's those 3 elements. You produce 44.8 liters of CO2 and 36 grams of water. So what do I do first? Write what I think is a reaction. Now, this is not balanced, right? All I'm doing is what's called a skeleton equation. The reason I want to do this is because I want to see what's going on. So I know I have 36 grams of this. O2, I don't have a mass for, right? CO2, I have 44.8 liters. 36 grams of this. And the reason I do this is because I want to organize my data. I want to see what's going on. And I will suggest doing this because anytime you're burning, the other reactant is just going to be O2. Pretty easy. So since the moles of an element are on the product side must equal the moles on the reactant side, what you could do right now is that if you're trying to figure out the identity of this, if I could get my moles of this, and the moles of O from here, which is from here and here, right? I could theoretically get the moles of these 3 elements, because why? However many moles of the element you have on the product side, you must have on the reactant side. So if I have the moles of all 3 of these, I could go to step 3 of the empirical formula and solve for it, make the question really easy. All right, so first thing we're going to do is go from moles of carbon from the CO2. So we're going to get our moles of C by first figuring out how many moles of carbon are in CO2. Then we're going to get the moles of H from H2O. And then the hardest part, we're going to get our moles of oxygen. Now, I could theoretically get my moles from here and here, add them together, and then go here. But the problem is that there's 2 different sources of O. On the left side and the right, that's going to be a headache. So here's a better play. Get your grams of oxygen here. Get your grams of oxygen. No, I'm sorry, that'll make it more time consuming as well. That'd be a bad route as well. Let's try a different route. The better route would be if you know your grams of carbon, you know your grams of hydrogen, and you know your total mass of the sample, I could take 36 minus those two masses, and what's left is going to be the oxygen. So that's the fastest way. The other ways you could do, just be more time consuming. I'm going to show you how to do that. And then you step 3 and 4, the empirical formula setup we saw a minute ago, and then we could solve for it. So here's our moles of CO2. There's 22.4 liters in a mole, right? 2 moles of CO2. We're going to go from CO2 to carbon using stoichiometry within the compound. And this is the most common calculation stoichiometry within the compound. Just be aware of that. All right, so let's make our T-chart look a little cleaner. Should have done it here too. But anyways, so in every 1 mole of CO2, there's 1 mole of carbon. So now you have 2 moles of carbon. Now I have one of the 3 moles. So there's 2 moles of carbon. That's going to be the mole value we do in step 3, right? Now we're going to do the same thing for hydrogen. Divide by the 18, which is the molar mass, get 2 moles of H2O. I need to go from H2O to H, so there's 4 moles of this. So I have 2 moles of this and I have 4 moles of H. How do I get my moles of O? Well, if I could go to grams of this and grams of this, so 2 times 12 is what, 24. 4 times 1 is 4. So you kind of eyeball this, so 24 plus 4 is 28. So 36 minus 28, get about 8 grams of O, right? So I'm going to show it to you in more detail. So here's your 24 grams of carbon, 4 grams of hydrogen, add them together. That gives you 28 grams. Now, if we subtract 36 by these masses from the carbon and hydrogen, we get our oxygen, which is going to be 8 grams. So now we have grams of oxygen, but that's not what I want, right? I have moles, moles. I want moles of oxygen too. So how do I do that? Divide by the molar mass, which is 16. So now I have 3 mole values. Now I could go and do the empirical formula setup from step 3 and beyond and get the identity of this unknown chemical. So 2, 4, and 0.5. This is obviously the smallest one, so I'm going to divide everything by 0.5. So I get 4 moles of carbon, 8 moles of hydrogen, 1 mole of oxygen. So good news is I don't have to multiply by anything because they're all whole numbers. So it'll be what, C4H8O. That's my empirical formula. Seems like a lot of work. And this is a really complicated question you need to be familiar with. And this is one I would make sure you understand. So you're trying to get the moles of the unknown from the moles of the chemicals they give you. And that's the most common route. The added twist was getting the O, right? Because you couldn't do that, you know, mass of the element on the product side equal on the reactant side because there's too much going on, right? So this is a really complicated question in that you had to do that last step, which is get your masses of the 2 other elements inside the compound to figure out the third one. Very important question. All right, moles and gases. When asked for moles of a gas while giving temperature and pressure, use what's called PivNerd. So I'm just going to introduce this to you and come back to it later in the gas law. So pressure is an atmosphere. This is the relationship. There's 760 millimeters of mercury in 1 atmosphere. You need to know this relationship because they'll give you millimeters of mercury, but in order to do this calculation, you'll need to be in atmosphere. So how do you do that? Take the pressure to give you millimeters of mercury, divide it by the 760, and you get atmospheres. And that's what you're looking for. R is 0.0821. Temperature is always going to have to be in Kelvin. So what you have to do is take your Celsius temperature, add 273, and that gives you your Kelvin temperature. This is always the case, so there's no way around that. And as your moles of gas. So how many liters of 3 moles of helium gas is present in a container at 27 degrees Celsius and 1 atmosphere? So I have my PivNerd, right? So which values do I have? I have my moles. I have my R, because that's a constant, so it's going to be 0.0821. Temperature, I'm going to change this to Kelvin, so about 300. I have my pressure, which is 1 atmosphere, so I'm looking for V. So basically your formula becomes this, nRT over P. So here's my pressure, there's my temperature, and those are the calculations. Plugging in 3 moles times 0.0821 times 300 divided by my pressure gives my volume, which is 73.8 liters. So that's my answer. That's how you do it. So when you're dealing with a gas and they're asking you for liters, moles, pressure, or volume, it's going to be this formula. Later on, we'll find out some other gas law formulas and we'll deal with those later. But for now, this is going to be your play when you're dealing with gas and they're looking for any of these following, right? Temperature, moles, pressure, or volume. So keep that in mind in your playbook. All right, the last thing we're going to go over is molarity and titration. So molarity, also known as concentration. basically the moles of the chemical per liter of solution. So what you're doing is figuring out how much of the solute is inside the solvent. There's your formula, moles of solute per liter of solution. So what is the molarity of a solution prepared by dissolving 11.5 grams of NaOH in enough water to make 1.5 liters? So in order to do this calculation, I need moles and I need liters. Well, good news, they gave me volume. So there's my liters. How do I get moles? Divide this by the molar mass, which basically is 11.5 divided by the molar mass of that, which is 40 grams and 1 mole. And that'll give you your answer. So which is 0.288 moles. Molarity equals, and please get in the habit of writing the formula first, then plugging in the numbers and then solving. So 0.288 divided by 1.5 liters gives my molarity. So this is how concentrated it is, which is a very small number in this situation. It's not very concentrated at all. All right, concentration of ions, determine the concentration of ions. So now that you know how to do concentration, how do you get the concentration of ions inside of a chemical? So this has 0.5 molar. So what's the concentration of cobalt? Just use stoichiometry. What's the ratio of cobalt to cobalt nitrate? 1 to 1, right? There's 1 cobalt ion per 1 cobalt nitrate solution. So it's basically going to be 0.5 molar for the cobalt. For nitrate, there's 2 for every 1 cobalt. So what's the ratio going to be? 1.00. So there's your difference. So notice my little T chart again, a variation of it using multiplication. You could do either one, doesn't matter. So 0.5 multiplied by the ratio, you get 0.5 molar of cobalt. Do it for nitrate, you get the molarity of nitrate, which is 1 molar. So that's how you do concentration of ions. All you have to do is just take the ratio. Now, if you didn't draw the products, not a big deal. Use the subscripts as your values, right? There's 1 cobalt for every 2 nitrates. So if I have, for example, let's say calcium phosphate, right? So my ratio would be 2 phosphates and 3 calciums. I don't need to write a balanced equation or write the products to know that. I know it's going to be 2 phosphates here and 3 calciums. So keep that in mind to make that a little easier for yourself. All right, so answer the following for 1 molar of iron 3 perchlorate. So you could once again do the reaction if you wanted to, or just look at it. 3 perchlorates. So the concentration of perchlorate I already know is going to be 3 molar. What's the concentration of iron? 1 molar, same value. Why? The ratio 1 to 1, and then for perchlorate 3 to 1. So that's how you get 3 molar of ClO4 minus. So that's how you do concentration of ions. Another variation of stoichiometry. Dilutions, process of making a solution less concentrated by adding more solvent, adding more water to water it down. Here's your formula for molarity. M1 is concentration you start with. V1 is whatever you're given initially, the concentration, whatever you're given. M2 is the concentration you want, what you're looking for. And V2 is the volume you want. So the vast majority of the time, you're looking for V1. And if you're not looking for V1, you're looking for the volume of water you're adding, which is going to also require you to do a little bit more math, but we'll talk about that when we look at one of those. All right, so how do you make 500 milliliters of 1 molar acetic acid from a stock solution of 17.4 molars? So let's label these parts. This is our M1, it's your stock solution, right? Whatever you start with is your M1. If you have a hard time figuring it out, it's the one that doesn't have a volume attached. That's usually your M1. This is your V2, because that's what you're looking for. That's your M2. So what am I looking for in a situation? V1. Well, you're looking for a little bit more than that, but we'll talk about it as we go through the question. So there's your values. M1 V1 equals M2 V2. So I'm going to plug in my numbers. 28.7 milliliters is your volume that you need to add. So what this basically means in English is that you're going to take 28.7 milliliters of this 17.4 molar full acetic acid, and you're going to add water to it until you get 500 milliliters, and then that's going to give you a concentration of 1 molar. So since the total volume you need is 500 milliliters, just the way you want to look at it. Let's say you're doing a volumetric flask, for example, right? You're going to take 28.7 milliliters of this, 28.7 milliliters of this acid. So this is acetic acid, which is HC2H3O2. So you're going to use a graduated cylinder, measure that volume, and pour it in. And realistically, you shouldn't pour that in first. I should correct myself, because you always want to add acid to water, never water to acid. If you add water to acid, what's going to happen? The water is going to instantly vaporize because of the high temperature generated by this reaction. It'll come back and hit you. So never add the acid first. So scratch that. So what we're going to do, we know we need a certain volume of water. So how much water do we need? Well, the total volume, when this is all said and done, is 500 milliliters, right? How much acid are we adding? 28.7. So that means we need 471.3 milliliters of H2O, because that's how you do a dilution. So you're going to fill this up with 71.3 milliliters of water, and then you're going to add 28.7 milliliters of your acid, and that's going to create the dilution you're looking for. So now you're going to have 500 milliliters of this solution. It's going to have exactly concentration of 1 molar. So that's how you make that solution. All right, the final thing is titration, which in chemistry is used to figure out the concentration of an unknown chemical. Basically something you could do in lab to figure out the concentration of anything. And there's different types. There's acid-base titration, there's redox titration. We're just going to talk about acid-base for now. All right, the first thing you want to do is write a balance equation for the reaction, where they're really giving you. Calculate the moles of the reactant for which you have both the molarity, both the molarity and the volume for, and this will make sense once you see it. 3, divide the moles from step 2, which is right above it, by the coefficient for that chemical, so kind of like stoichiometry, right? Step 2 for that. And then multiply the answer from 3 by coefficient to reactant you're looking for. So these two are basically, if you look at it carefully, these are like step 2 and step 3 for stoic. And then finally divide the moles you determine in step 4 by the chemical's volume to determine the molarity. So let's go through this. So here's an example. You have 30 milliliters of 0.1 molar NaOH neutralized 25 milliliters. So here's your acid, here's your base. So you're going to react these two, right? Typical acid-base reaction. You're not doing it ionic, so please don't get rid of any chemicals. You're going to write the complete reaction with all chemicals showing. So for NaOH and plus HCl, you get NaCl and H2O as your products. So step 2, after you write your balance equation, what I'm going to do is sit here and multiply my molarity and the volume by what I'm given. So here's your volume, here's your molarity. Now you need to change to liters, right? You don't want to use this in milliliters, because if you remember 0.30, let's just keep it as 30 milliliters to show you what could have gone wrong. This is basically 0.10 moles, per 1 liter of solution. Notice milliliters and liters don't count, so that's why you can't do this. That's why you have to go into having the value as liters, so that way the units cancel out. Once again, the usefulness of the T-charts to help you avoid these kind of brain farts. So I'm going to multiply the molarity to volume by whatever they're giving me, get my moles of NaOH. So I have moles of this. I'm going to go from moles of this to moles of this. So the way I do that, I'm going to divide the moles from 2 by the coefficient of chemical. So what's the coefficient for NaOH? 1, right? Because there's nothing in front of it. Same thing for HCl, it's 1. So now I have moles. You have 3 times 10 to the 3 moles of NaOH. And then you're going to take that, and realistically, these moles should cancel out too. So you should just be left with, because if you looked at it carefully, this goes away. So you just have a number. It's like you would in step 2 of stoichiometry. You're going to take 3 times 10 to the negative 3 and multiply by the moles of whatever you're looking for. So what am I looking for in this situation? I'm looking for HCl. So I multiply by the 1 for HCl. Now what do? You take this number, and you divide it by the volume of that solution. So here's what you basically did. At neutralization, the moles of NaOH equals the moles of HCl, stoichiometrically. So this balance equation allows you to go between moles of one chemical to another only at neutralization point, the part where the two chemicals are equal to each other. And then you're going to take that information and, using this setup, figure out the moles of this unknown chemical, because from there you can figure out the molarity. So the molarity is just going to be the 3 times 10 to the negative 3, just figure it out in step 4, by the volume of HCl they gave you, which if you look back was 25 milliliters, which is basically 0.025 liters. And there's your answer. So that's the molarity of an unknown using titration. Let's try it one more time just to make sure you understand it. And something a little harder too. You have 25 milliliters of barium hydroxide neutralized 40 milliliters of nitric acid. So you can determine the concentration. So what's the first thing you need to do? Write a balance equation. So here it's a 2-to-1 ratio. So you already know this question is going to be a little more interesting than the one before. Step 2, multiply the molarity times the volume of what they're giving you. They're giving you these two up here. So change that volume to liters and then multiply. So you get 1.25 times negative 3 moles of barium hydroxide just by multiplying the molarity times the volume. Divide whatever you got here by the coefficient, which for barium hydroxide is just a 1. That's easy. You get just a number. And then step 4, multiply whatever you got in step 3 by the coefficient which you're looking for. I'm looking for HNO3, right? That's, you're always going between one chemical and another. So here you multiply by 2, and you get 2.5 times negative 3 moles of HNO3. So now you have moles on HNO3. The difference here was there wasn't a 1-to-1 ratio, right? So it was a little bit more difficult because you had to actually multiply by something in step 4. And then finally divide by the volume, which is 0.04 liters, which in case you didn't notice, was the original volume of this acid. So what I basically did, I figured out what the concentration of this acid was from the beginning. And that's what you're trying to do, figure out the concentration of an unknown chemical. All right, so that was stoichiometry. Hopefully you have a little better understanding of it, and you'll be able to do some of the math and the calculations.